Hello everyone, so in this video we're going to focus on combustion analysis, specifically how to determine the empirical formula of a compound. So our first question is, what is combustion analysis? Combustion analysis is a chemical technique where we are going to determine the empirical formula of some organic compound by burning it. So in this apparatus we have three separate chambers, and these chambers are connected, and a carrier gas, oxygen, is going to be running through it. The reason why we use oxygen is because that is one of the necessary reactants in order for combustion to occur in the furnace. The other necessary reactant is the fuel, which is our organic compound that we're burning. So through combustion, we're going to form two major products. We're going to make carbon dioxide and water. The oxygen that comes out of this chamber is anything residual from the carrier gas. The other gases is going to come from whatever other elements besides carbon and hydrogen that were in our original sample. So in our second chamber, we have a water absorber. So in this chamber, we're going to be taking the water out of that combination of gases, and we're going to weigh it. In our next chamber, it's the same thing, but instead of water, we're going to be absorbing carbon dioxide. So what happens is, after going through those two chambers, all we have left are the oxygen and other gases, which are just vented out of the apparatus completely. So what we're going to do is we're going to take the data that we got from the mass of water and the mass of carbon dioxide, and we're going to break it down to determine the percent composition of those elements in our original compound. The next question we have to ask ourselves is, what types of compounds can be used in combustion analysis? And the first type are simple hydrocarbons. Hydrocarbons are things that contain hydrogen and carbon. So anything like methane, CH4. That is a hydrocarbon. It has carbon and hydrogen in it. There are other more complex organic compounds that have carbon, hydrogen, and then other elements. Things like carbohydrates have carbon, hydrogen, and oxygen. You can throw a bunch of other things in here like chlorine, nitrogen, sulfur. Pretty much any element you can think of, you can also use for combustion analysis, as long as it has carbon and hydrogen. It just might be a little more complex to do that. So we're going to start by looking at what to do with simple hydrocarbons, and then look at more complex problems with other elements. In the analysis of simple hydrocarbons, we have four major steps. The first step is to determine the grams of carbon from the CO2 we collected in the third chamber, and the grams of hydrogen from the water we collected in the second chamber. From that information, we're going to determine the number of moles of carbon and hydrogen. This is using stoichiometry and dimensional analysis. In the third step, we're going to divide by the smallest number of moles. What this is going to do is it's going to give us the ratio of the elements in the compound to determine our empirical formula. The fourth step is an if needed step. Now, if when we divide by the smallest number of moles, we do not get a whole number, we can't have fractions or decimals in the subscripts of a chemical formula. So what we will need to do is we're going to need to multiply by an integer until all of the numbers are whole. Right? So in our next slide, we're going to do an example of this. A 1.50 gram hydrocarbon undergoes complete combustion to produce 4.40 grams of CO2 and 2.70 grams water. What is the empirical formula of this compound? So our first step is going to be to determine the grams of carbon from the carbon dioxide and the grams of hydrogen from the water. How we're going to do this is we're going to start by taking the 4.40 grams of CO2, and we're going to set up dimensional analysis. So what we're going to say is, well, for every mole of this CO2, so 1 mole of CO2 is 44.01 grams. For every mole of CO2, you can see there's 1 mole of carbon in it. Well, 1 mole of carbon is 12.01 grams. Right, that's carbon. So for every 44.01 grams of CO2, we have 12.01 grams of carbon. So when we do this dimensional analysis, we find that there is 1.20 grams of carbon in our particular sample. Right? We can do the same thing with the water. We're going to take the 2.70 grams of H2O. Right? On the bottom, we're going to have the molar mass of the water, 18.02 grams. And on the top, notice for every 1 molecule of water, we actually have 2 moles of hydrogen. So instead of using the molar mass of hydrogen, 1.01, we need to multiply that by 2. So we get 2.02 grams of hydrogen. So in this amount of water, we end up having 0.30 grams hydrogen. Now when you look at these two masses, if we were to add them together, so 1.20 plus 0.30, we end up getting 1.50 grams. And you'll notice that that is the exact same as our original amount of hydrocarbon. This is good. It means that the amount of carbon and hydrogen we have adds up to our total compound. We're not missing anything here. So we can move on to our second step, which is going to be to find the number of moles. This is simple stoichiometry, where we're going to take the 1.20 grams of carbon, and every 12.01 grams is 1 mole. Right? So 1.20 divided by 12.01 gives me 0.0999 moles. I can do the same thing from the hydrogen, 0.30 grams of hydrogen. Now in this case, I am dealing with just 1 mole of hydrogen, so I can use the 1.01 grams in 1 mole. That is going to give me 0.2970 moles. Our third step now is going to be divide by the smallest number of moles. Well, looking at these two numbers, the 0.999 is the smaller number. So I'm going to divide both by 0.0999. So here the same number divided by itself is going to give me 1, and 0.2970 divided by 0.0999 ends up giving me 2.97. That is close enough within reason. I'm going to approximate that to a whole number 3. Right? 2.97 is very, very close to 3. So that tells me for every 1 carbon, I have 3 hydrogens. So my empirical formula is CH3. Now, analyzing compounds with other elements ends up being more complex. We've added a step here, and the step we've added is number 2. Right? So right after we've determined the grams of carbon and hydrogen from our chambers 2 and 3, okay, we're going to have to subtract those grams from the total mass to determine the mass of the other elements. I don't have a way of analyzing the other gases. Remember, those are just spat out at the end. So what I'm going to have to do is subtract it from the total so I know how much is left over. That must be from the other elements that were in the original compounds. So from there, everything is the same. I'm going to determine the number of moles of carbon, hydrogen, other elements, divide by the smallest. If needed, I'm going to multiply by an integer until they're whole. So let's do some examples with that. Caproic acid is a carbohydrate that causes socks to smell. If you combust 0.225 grams of this acid, you get 0.512 grams of CO2 and 0.211 grams of H2O. What is the empirical formula of the caproic acid? Well, the main point that you got to see right here is the fact that it is a carbohydrate. If it is a carbohydrate, it is made up of carbon, hydrogen, and oxygen. So we are going to work with that information. We know how to get the carbon and the hydrogen, and we're going to subtract from the total mass to find that remaining oxygen. So the beginning part here is going to be much the same as before. I'm going to start with 0.512 grams of CO2. For every 44.01 grams of CO2, I get 12.01 grams of carbon. So that math is going to give me 0.140 grams carbon. Now I'm going to do this for the water. So I've got 0.211 grams of H2O. For every 18.02 grams of water, I get 2.02 grams of hydrogen. Remember, it's 2.02 because there are 2 moles of hydrogen for every 1 mole of water. Right? So in this particular sample, I've got 0.024 grams of hydrogen. Now, if I add these two together, so 0.140 plus 0.024, I get 0.164 grams. Right? Now, notice in my original compound, it was 0.225 grams. Something was missing. That's the oxygen. So to find the mass of the oxygen, I'm going to take 0.225 grams, my total mass, and I'm going to subtract out the 1.64 grams. That leaves me with 0.0 0.61 grams oxygen. Right? So I've got carbon, I've got hydrogen, I've got oxygen. Now I can move on to the next step where I'm going to convert all of those to moles. So starting with 0.14 grams of carbon, every 12.01 grams is 1 mole. That means I have a total of 0.012 moles of carbon. For the hydrogen, I've got 0.024 grams of hydrogen. For every 1.01 grams, that is 1 mole. That gives me 0.024 moles. And finally, the oxygen, I've got 0.061 grams of oxygen. Now, the molar mass of oxygen is 16 grams for 1 mole. That gives me 0.004 moles. Now, the smallest one here is the 0.004, so I'm going to divide each of these by 0.004. So for the carbon, I get 3. For the hydrogen, I get 6. And for the oxygen, I get 1. Those are all whole numbers. I don't need to do any multiplication. This is great because it means my compound is C3H6O. And that is the empirical formula for caproic acid. For our final example, I've got a bit of a monster, and I'm going to show you why and how we're going to handle it. So this problem says the combustion of 1.38 grams of a compound which contains carbon, hydrogen, oxygen, and nitrogen yields 1.72 grams of CO2 and 1.18 grams of H2O. Another sample of the compound with a mass of 22.34 grams is found to contain 6.75 grams of oxygen. What is the empirical formula of the compound? The reason why this is so difficult is because we've got carbon, hydrogen, oxygen, and nitrogen. That means that we have not one other element, but 2. So the simple subtraction from the total mass isn't really going to help us all that much because we can't narrow it down to belonging to just one element. It's going to be a combination of the oxygen and the nitrogen. So we're going to have to do something else for one of those before we can get the last one. So we're still going to handle the carbon and the hydrogen the exact same way. I'm going to start with 1.72 grams of the CO2. For every 44.01 grams, I've got 12.01 grams of carbon. Right? So that gives me 0.469 grams of carbon. Now I'm going to take the water. 1.18 grams of H2O. Molar mass of water is 18.02. The 2 moles of hydrogen there is 2.02 grams. That means that I have 0.132 grams of hydrogen. All right, carbon and hydrogen out of the way. Now the key here is the fact that it says another sample of the compound. Now this sample had a mass of 22.34 grams and it contained 6.75 grams of oxygen. All right, so I'm going to use an alternative method to calculate my grams of oxygen in the sample that I combusted. And how I'm going to do this is through dimensional analysis, but it's thinking about dimensional analysis in a completely different way than we have before. I'm going to take 1.38 grams, and this is from my original compound. Okay. What I'm going to say is, right, in this new compound, right, so this other sample that I took, there were 22.34 grams of the compound. And in those 22.34 grams, I had 6.75 grams of oxygen. It is setting up a new conversion factor using some other experiment. So if I had 6.75 grams of oxygen in this 22.34 gram compound using ratios, how much oxygen is that going to be in my 1.38 grams? So 1.38 times 6.75 divided by 22.34, that is going to give me 0.417 grams of oxygen. Another way to think about this part is basically the same as saying, well, what percent of oxygen is in the compound, and then taking that percentage out of my 1.38 grams. You can do it that way too, whatever works. So now what I'm going to do is I'm going to take all 3 of these guys, All right, so my carbon, hydrogen, and oxygen, remember I'm still missing that nitrogen. I'm going to add these up. So 0.469 plus 1.32 plus 0.417, it gives me 1.018 grams. Okay, notice that still does not satisfy my original 1.38 grams. So I'm going to take my 1.38 grams, I'm going to subtract out the 1.018 grams, and that is going to leave me with 0.362 grams of nitrogen. Now I have all four of my elements, carbon, hydrogen, oxygen, and nitrogen, and I can move on to the next step of determining the number of moles. Now I'm going to do that from this slide just so that I have enough room. I've listed those grams we just calculated underneath the original question. I'm going to start with carbon here. So I've got 0.469 grams of carbon. Right? Molar mass is 12.01 grams per mole. That means that I have 0.039 moles. Right? Now I've got 0.132 grams of hydrogen, 1.01 grams per mole. That means that I have 0.131 moles of hydrogen. Next up is oxygen. I've got 0.417 grams of oxygen. Molar mass is 16 grams per mole. So I've got 0.026 moles of oxygen. And last we've got our nitrogen. So I've got 0.362 grams of nitrogen. Molar mass of nitrogen is 14.01 grams per mole. And that also gives me 0.026 moles. So the smallest number here is that 0.026, and yes, I do have it on here twice. So 0.026 divided by 0.026, and we're going to do it again one more time. These guys down here are easy. They are both 1, dividing the same number by itself. The 0.039 divided by 0.026 gives me 1.5. 0.131 divided by 0.026 gives me 5. I have a problem here. Right? This 1.5 I cannot use. I cannot have a decimal as the subscript in an empirical formula. So the only way to get a half to a whole number is I'm going to have to multiply it by 2, but I can't just multiply one of them by 2. I have to multiply every single one of these numbers by 2. So I've got new things. 1.5 times 2, that's going to be 3. 5 times 2 is 10. 1 times 2 is 2. 1 times 2 is still 2. Right? So looking at this now, I've got C3H10, O2, N2, and I am done. So that is combustion analysis and how you can solve the multitude of problems that come off of it.